Okay, we'll be getting started. So last class we went over inequalities and we went into squares of binomials. If anyone wants a review on that, they can just ask me or watch the recording of it. So I'll be going on. So difference of squares. So first of all, this whole lesson is on more than one variable factorization. So it's so they're rather specific maybe, but regardless. So x squared minus y squared. This is a difference of squares, and I've talked about this before, but if we multiply x plus y times x minus y and multiply it out, we get this, which is what is meant by factoring the difference of squares. Anyways, this is useful in a few senses. So first off, let's say we have this. Well, this is irrational. And however, if we multiply it by this, by x minus y, x plus y, this becomes x minus y squared, or 3. When we do this, it's by multiplying one radical by negative. So say -7 minus 5. This product is 2. So it provides a simple way of getting rid of radicals. But there are more subtle uses, like using the difference of squares. What does this equal? Also, this -4 is under the radical. Hold on. So can anyone tell me what this is? By using the difference of squares, it's easily solvable without a calculator. Think about how the difference of squares could be useful here. Anyone? It's fine if you're wrong. I would just appreciate participation. Well, first off, this is 195,674 minus 2, and this is 19564 no, this should be plus 4. That's my bad. This is 7, 4 plus 2. So we have this minus times this. And so these two cancel out. So, and these, the radical and the square cancel out. So this is our final answer. So I'm using a mouse right now, so, but I use the text if I'm writing out a problem. So factorization of cubes, we're still on 2 variables. So a common pattern you will see is that this is x3 minus 1, and this is x3 minus 8. Following this, can someone tell me what x minus 3 x squared plus 3x plus 9 is? Yeah, exactly. It's x3 minus 27. So we have a general pattern here. So if we denote this as y, then x minus y times x squared plus x y plus y squared is equal to x cubed minus y cubed. Now, what if we had x cubed plus y cubed? Well, y cubed is plus y cubed, I should say, is negative y cubed, since 4 negatives cancel out. So we just replace everything here with negative y. So x minus negative y becomes plus y. X squared remains. Y is negative. Y squared remains. And we have x cubed plus y cubed. An interesting thing about this property is that you can project it upwards. So, such as so we have x and y to the 4th power now. So first off, no, this won't work. It has to be to the 5th. So 5th power. If you go to x to the 4th power, neither x or plus y or x minus y divide this, because this basically means that x equals negative y as a solution if this were to be 0, and similarly for this, but they don't work unless x or y is 0, which is kind of a false solution. So we must go with, or we could go with -4 actually. So you can factor by a negative y because x equals y is the solution of this being 0. And oh, so factoring. Using more than 2 variables is kind of you kind of have to get the terms you have and then use variables to find which terms will become it. So in this scenario, we'll have terms x3, y3, which will be plus because this times this is negative, and we'll have x squared and y squared, yx squared and xy squared. This is because we know that all the terms here have to be to the third power of a sum, and that these two aren't enough. So I'm actually doing calculations on this spot, so forgive me for being a bit slow. Excuse me, this should be plus. X minus y also factors out, but x plus y is cleaner and also works with x equals 0. And this becomes y minus 3, and we have a similar format. It goes down a y minus, goes down an x power, and replaces it with a y. Goes down another x, replaces it with a y. I'll check that this actually works. Yeah, this is the actual formula. Returning back to this, the point is that it goes upwards. This should be minus. X2n plus 1 plus y2n plus 1 equals x plus y xn 2n minus x2n minus 1y, etc., etc. So it's not just for cubes, it's a general concept that goes forward. And there's a similar formula for squares, I believe, but only as this as negative. This formula works as both plus and negative because a negative inputted into y or x will flip it from a sum or a difference. And using this cube difference, which is 32 t cubed minus 108. So this is a bit of a tangent, but I'll talk as you guys work. But there's actually a more specific factorization that's more glossed over because it's really specific. This is 2. But this equals, I don't know what this is called, but it's called after someone. It's just a neat factorization trick that's less touched upon. But regardless, can anyone solve this? If you look here, it actually uses square differences, but with these two as a whole and 2xy as positive and negative. Am I going too quickly? If so, feel free to ask any questions. Or any concerns. Okay, so first off, we need to get this into the form x3 minus y3 plus or minus doesn't matter. But 32 is not a cube, and honestly, cubing 32 is not what we want to do. So, but these two share a common factor of 4. And now we see that 8 and 27 are both cubes, so we can just use the formula we had before, except with 2t and 3. So 4t cubed is squared minus, plus 6t plus 9 with a 4 as at the end. So rationalizing the denominator. So if you're writing math like in a public sense, or maybe in even a school sense, this is usually frowned upon because there's a radical and irrational, I should say, in the denominator. So what you want to do is rationalize the denominator. What I mean by this is that whatever's on the bottom of the fraction should be integer, or it should be rational. So how do we do this? So first off, what is square root 2? It is 2 to the half. And by power, we know that it's 2 to the over square root 2, since this is 1, this is half. Since 2 halves equal 1, so we can write this as 2 over square root 2. And now this is better looking than what we had here. Okay, and similarly, if you had something like this, you can do this. Moreover, if you do something like this is not an integer because it's a cube root. You can multiply this by 4/3 squared, which would also equal 16 cube rooted. This would be 4 because 3 cube roots is the original, whatever's under here. But this is all fine and dandy until we get to something like this. So how do we get around this? Does anyone have any ideas? I mean, I hope I'm not just talking to myself. Okay, so if we multiply this, the bottom, by, as we did before with difference of squares, we get this. Now you can see how we can push the bottom to the top. What about, well, first this seems scary, it's cube root. However, we can use the same principles we used before, multiply this by square root 3 minus 1. So as you can see, rationalizing the denominator often uses techniques we just learned about, two variable factorization. And okay, so this is a bit more complex. There are 3 radicals. If we try to do this, we still have radicals we still have to eliminate. However, it is a good stepping stone since it eliminates a few radicals. So and some difference of squares, -5 plus 13, and radical, which is 8 plus 242, and we can cross out common factors to make our lives easier. So what about this? Well, we can just use it again. Nothing's stopping us. So, and when we have this, a constant with a radical, we can just minus the radicals since it's basically the same principle. I'm not going to expand this, but I hope you guys get the point. Okay, so Simon's favorite factoring trick. So let's say we have this. If it's so x was extremely hard for us. This isn't really, it's a very huge obstacle, but on the plus side, x and y are positive integers, which is a Diophantine. I white text for this Diophantine equation where solutions are integers. They will be positive here, but integers. So how can we use this? Well, we want to factor this in a way such that it's easy to find the solutions. So let's try factoring out x. No, this should be the opposite order if I were factoring x. Okay, but we still leave out this y and this 76, which is less important to include. But y plus 1, what if we added 1 here? Now we could do y plus 1, x plus 1 equals 77. Well, now this is easy because it's a number times a number equals 77, and there are only so many numbers such that multiply into 77. In fact, given that you can't have 1 as one of these sets, they have to be positive. There are only 11 and 7 that multiply these into this. So this has 11, this is 7, this is 6, 10. If you do it the other way, it's 10, 6. Okay, how about we try with something? So this trick is called Simon's factoring trick, which is named after Simon Rubin Sazedo. I don't think they're historical though. I also probably butchered the pronunciation. But what if we did this? So at first glance, this isn't what we would use this for. But if we were to multiply m and n out and push it over to one side because that's easier, we have the form of it at least. So let's first factor out n as we did before. So we need to find a way to get m minus 4 on this side, or well, with the 2m we have left over. So we need it to be something like this. So this is our angle. So all we have to do is compensate for it. Reminder that the number of m's have to stay the same. So what did we do to get here? So what does this equal? Minus 2m plus 8. So we added 8 to get here. So we have to add 8 on the other side as well, which is compensation for what we did. So n minus 2, m minus 4 equals 8. Now, just setting this as positive integers, the solutions to this are 1, 8, by a bit of a stretch, -1, 8, I meant the numbers. Actually, never mind. -1, 8 isn't possible. For 2, and these are the only pairs that are possible from this configuration. So if we put them in and switch it around, we get that the final answers are 3, 12, ten, 5, 6, 6, and 4, 8. If we look back on this one, the original equation, this does not work. This does work. This works. Never mind, this does work. This is 4, 8. This does work. So it's good to check up on your original equation in case it doesn't work. In this case, it did work. Don't know if it would ever not work, but it's good to check. So I finished with the factorization. So I'll go on to the next lesson for around 20 minutes or so. That's so we could cover material faster. This is labeled day 12, but I'll go into it now that we finished early. So functions. I've talked about this before, but they're kind of like a machine that you function. I'll just write F for function. Input I, output O. And this does something. So if we put X as our input, the corresponding output would be Fx, or it's usually undercase F, just as a bit of convention. You can usually write functions as any letter though. G, H are usually, F, G, H are usually the main ones. G after F, H after G. But when two inputs can correspond to the same output, but the same input can't correspond to more than one output, since this creates uncertainty. You don't know which output to go to. with that out of the way, let's say this side is the inputs, and this side is the outputs. Oh, yo, this is a 9, by the way. 11, 13. Let's say the function here is me drawing lines. The lines mean corresponding things. Is this a function? Okay, so 4 diverts into 5 and 6. So you don't know if input of 4 would go to 5 or 6. So this is not a function. I'll end the class here because you guys don't seem very active. So I'll end it here, and it's also because I'm getting a bit tired as well. So let's end it here.